All right, so have you ever stared up at the night sky and just thought about what was there before the Big Bang? I mean, was it just nothing? Like seriously, nothing. It's a question that has puzzled philosophers and scientists, for forever. And today we're going to dive deep into this mystery and kind of explore how our understanding of the universe has evolved over time. We're going to be taking a journey through some pretty mind-bending concepts from Stephen Hawking's A Brief History of Time, a book that outsold, get this, Madonna's book on sex. It's pretty wild when you think about it. It makes you wonder what people are really thinking about late at night, right? But let's start, at the beginning with the ancient Greeks. I mean, those guys were sharp, really sharp. They looked up at the stars and just use their powers of observation to come up with some really, really clever ideas about the universe. For example, they figured out that the Earth was round, not flat. I remember reading about this in college, and I was just like, whoa, how did they do that without spaceships and satellites and all that? They really had some tricks up their sleeve.
Take Aristotle, that famous philosopher dude. He noticed how ships sailing over the horizon would disappear hull first. And during lunar eclipses, get this, the Earth's shadow on the moon was always curved. And then there's the North Star. It appeared at different angles in the sky depending on how far north or south you were. So putting all those clues together, they deduced that the Earth had to be a sphere. Pretty impressive, right? But the Greeks also thought that the Earth was at the center of everything, the center of the universe, with everything else revolving around it. This was called the geocentric model. And, it made sense to them at the time. After all, it looks like the sun is rising and setting and moving across the sky. Right. I can totally relate to that way of thinking. Remember when I was a kid, I used to think that the moon followed me around, like it was my own personal spotlight. It's kind of funny when you think about it. But the Greeks kind of did the same thing, but with the entire universe. And that geocentric view really held sway for centuries. It even got tied up with religious beliefs, which made it even harder to challenge. But then this guy Copernicus comes along in the 16th century, and he had this radical idea, really radical. What if just maybe the Earth wasn't the center of everything? Crazy thought, right? Copernicus proposed a different model, the heliocentric model, with the sun at the center and the Earth, and other planets orbiting around it. It was a huge shift in thinking. I mean, just imagine going up against centuries of ingrained belief. Copernicus had some serious guts. And you know what? It totally paved the way for a scientific revolution. And that revolution, well, it really kicked into gear with Isaac Newton in the 17th century.
Yeah.
The apple falling on the head guy, that's probably just a myth, but it makes for a good visual, right? Anyway, Newton came up with his laws of motion and universal gravitation, which explained how objects move and interact with each other. He showed that the same force that pulls an apple to the ground is the same force that keeps the planets in orbit around the sun. It's like this giant aha moment, connecting all these seemingly unrelated things under one, elegant framework. But even though Newton's work was revolutionary, he still believed in absolute space and time. He thought that time ticked by at the same rate everywhere in the universe. Regardless of your motion or your location, it's a kind of comforting thought, there's this big cosmic clock keeping everything in sync. But then in the early 20th century, this guy Albert Einstein comes along and just totally shakes things up. Einstein, with his, wild hair and crazy thought experiments, completely changes our understanding of space and time. He actually showed that time wasn't absolute, but relative, which is a really tough concept to wrap your head around. So imagine you're on this super fast train, traveling at nearly the speed of light. Inside the train, everything feels normal. You're just sitting there drinking your coffee, whatever. But to someone standing on a platform, time inside the train would seem to slow down. And the faster the train goes, the slower time seems to tick. It's totally like something out of a sci-fi movie, right? But that's how the universe works. Einstein showed that time is relative to your motion and where you are in a gravitational field. It's all wibbly-wobbly, timey-wimey stuff, just like in Doctor Who. And this idea of relative time, well, it has some pretty crazy consequences. It means that, Time travel, though tricky and paradoxical, might actually be possible. And this leads us to another one of Einstein's groundbreaking theories, general relativity. General relativity is all about gravity and how it works. It's not a simple force like Newton thought, but rather a curvature of space and time. Imagine a bowling ball and a trampoline. The ball warps the fabric of the trampoline, right, creating this like dip. That's kind of what massive objects do, like stars and planets. They create these gravitational wells that affect how other objects move around them. I'll admit, it's a pretty weird concept. I remember when I first came across this stuff in college, my brain basically melted. Trying to understand three-dimensional space is hard enough, let alone adding time as a fourth dimension and then bending it all with gravity. But the more you think about it, the more fascinating it becomes. And general relativity have been super successful in explaining all sorts of phenomena. Like, the bending of starlight around the sun and the existence of black holes. Those are those cosmic monsters where gravity is so strong that nothing, not even light, can escape. I remember watching this documentary about black holes, and it was just terrifying and awe-inspiring all at the same time. These objects are like rips in the fabric of space-time, like windows into the unknown. They raise all these crazy questions about the limits of what we know and the nature of reality itself. So we've come a long way from the earth-centered universe of the ancient Greeks to the totally mind-bending world of relativity and black holes. It's a journey full of surprises, and it just shows you that our understanding of the universe is always changing, always evolving, and we're really just getting started. So welcome back, to our cosmic adventure. Last time we were talking about how our view of the universe has totally transformed over time. We started with the ancient Greeks with their earth-centered model, then moved on to, Newton and his laws of gravity, and then bam, Einstein comes along and blows everyone's mind with relativity and all that crazy stuff. But there's even more mind-blowing stuff out there. Like the fact that the universe isn't just sitting still, it's actually expanding, like all the time. It's kind of freaky when you think about it, right? It's like, imagine a cosmic balloon, and it's constantly being inflated with all the galaxies, stuck to its surface. And as the balloon gets bigger, the galaxies move farther and farther apart. That's basically what's happening with our universe. So how do we figure this out? Well, we have this awesome astronomer, Edwin Hubble, to thank. Back in the 1920s, he was looking at these distant fuzzy patches of light through his telescope. We know now that those patches are actually galaxies, just like our own Milky Way. But back then, they were a total mystery. Anyway, Hubble noticed something really strange about the light coming from these galaxies. It was all shifted toward the red end of the spectrum. And this phenomenon is called redshift. It's kind of like, have you ever noticed how a siren sounds higher pitched when it's coming towards you and lower pitched as it moves away? It's called the Doppler effect. Well, it turns out that light waves behave in a similar way. As a light source moves away from us, the wavelengths of light, they get stretched out, and that makes the light appear redder. So Hubble observed that the farther away a galaxy was, the more redshifted its light was. And this could only mean one thing. The universe was expanding. All these galaxies were flying apart like pieces of cosmic shrapnel from some, giant explosion. And this whole idea of an expanding universe, well, it has some pretty big implications. I mean, for one thing, if we could rewind the cosmic clock, it would mean that everything was once much closer together, like really, really close together. In fact, if we go back far enough, like to the very beginning, it suggests that the entire universe was once crammed into this incredibly hot, dense point, a singularity. And then boom, it exploded outward and has been expanding and cooling ever since over billions and billions of years to form the universe we see today. And that, my friends, is basically the Big Bang Theory. It's like the prevailing model for how the universe began. It's a story of cosmic creation, this moment of unimaginable energy and expansion that gave birth to, well, everything. All the stars, galaxies, planets, even us. Of course, you might be thinking, okay, that's a cool story, but what actual evidence do we have for this Big Bang thing? And it turns out there's actually quite a bit. One piece of evidence is this faint afterglow of the Big Bang called the cosmic microwave background radiation. It's like this leftover heat from the universe's super hot birth, and it's literally everywhere we look in space. And then there's the abundance of light elements in the universe, like hydrogen and helium. The Big Bang model predicts the exact proportions of these elements that we actually observe, which is pretty amazing. It's like a cosmic fingerprint, a signature of the universe's fiery beginnings. But, even though the Big Bang model explains a lot, it still has its mysteries. Like, if the Big Bang was just this, random explosion, wouldn't we expect the universe to be all lumpy and uneven? But what we actually see is a surprisingly smooth and uniform cosmos. Like, the temperature of the cosmic background radiation is almost the same everywhere we look. So how do we explain this smoothness? Well, cosmologists came up with this idea called inflation. And it's like the Big Bang on steroids. It's this period of super duper rapid expansion that happened in the very early universe, like within a fraction of a second after the Big Bang. Imagine blowing up a balloon really, really fast. Any wrinkles or imperfections on the balloon's surface, they would get stretched out and become almost invisible. That's kind of what inflation did to the early universe. It basically smoothed out all the lumps and bumps, creating the uniform cosmos we observe today. But here's where things get even weirder. Inflation might have even created multiple universes, like a whole bunch of them, a multiverse. The idea is that, during inflation, different regions of space-time could have inflated at different rates, creating these like bubble universes, each one with its own set of physical laws and constants. It's like our universe is just one bubble in this, like giant cosmic bathtub full of infinite possibilities. Mind-boggling, right? But okay, let's come back to our universe, the one we call home. We know it's expanding, but what about its fate? Like, what's going to happen to it in the future? Will it expand forever? Will it eventually, collapse back on itself? Or is there some other, even more bizarre possibility waiting to be discovered? Well, the answer to that question really depends on, a few factors, like how much stuff, matter, and energy is actually in the universe. If there's enough stuff, gravity might eventually win the tug of war, slowing down the expansion and causing the universe to contract back into a singularity. It would be like the Big Bang in reverse, a cosmic implosion. But if there's not enough stuff, well, then the expansion might just continue forever, with galaxies drifting farther and farther apart, becoming these like isolated islands in this ever-expanding cosmic void. Kind of a lonely thought, huh? And then, of course, there's this Goldilocks scenario where the expansion slows down but never quite stops. The universe keeps getting bigger, but at a slower and slower rate, approaching a kind of a cosmic equilibrium. So which fate awaits our universe? The truth is, we don't know for sure yet. But trying to figure this out is one of the most exciting things about modern science. And speaking of mysteries, let's talk about one of the biggest head-scratchers of all time. We already talked about how Einstein revolutionized our understanding of time, showing that it's relative, not absolute. But there's another aspect of time that's even trippier, and that's the arrow of time. Like, why does time seem to move in only one direction, from past to present to future? Why can't we, unscramble an egg or unspill a glass of milk? Once something happens, it's done. This whole one-way flow of time is what we call the arrow of time, and it's a real puzzle for physicists because at the most fundamental level, like the laws of physics that govern how particles behave, they don't have a preferred direction for time. It's symmetrical. Imagine watching a movie of two billiard balls colliding. If you played the movie backward, it would look totally normal, right? The laws of physics work the same way, forward and backward in time. So why do we experience time moving in only one direction? Why can't we, hop in a time machine and visit the dinosaurs? Well, there are a few ideas out there. One idea has to do with the second law of thermodynamics. This law states that entropy, or disorder, always increases over time. Think about your room. It starts out all neat and tidy, right? Low entropy. But as time goes on, it naturally gets messier and more chaotic. Higher entropy. You never see your room spontaneously clean itself, do you? That would be a decrease in entropy, and it just doesn't happen. So maybe the arrow of time is connected to this ever-increasing entropy. Like maybe time flows in the direction of increasing disorder from more ordered past to a less ordered future. Kind of makes you think, right? But there are other arrows of time too, like there's the psychological arrow of time, which is basically our perception of time moving forward. We remember the past, but not the future. We can anticipate what's to come, but not what's already happened. And it's interesting to think about how the psychological arrow might be connected to the thermodynamic arrow. Our brains, after all, are physical systems, subject to the laws of physics, including that pesky second law of thermodynamics. So maybe our memories are like little pockets of order in this, like ever expanding universe of disorder. And maybe that's why we perceive time moving forward. We're moving along with the arrow of increasing entropy from a past of, relative order to a future of increasing chaos. I know it's all pretty mind-bending, and we're really just beginning to understand the complexities of how time, entropy, and our own perception of reality all fit together. But that's what makes this stuff so fascinating, right? It's a journey of discovery, and there's still so much we don't know. Okay, so welcome back to our deep dive into the universe. I feel like we've already traveled, billions of light years. We've gone from ancient Greece to Einstein and from the Big Bang to like the weirdest corners of quantum mechanics. We've talked about expanding universes, the birth of everything, and even that super trippy arrow of time. But hold on tight because things are about to get even weirder. Today we're stepping into like full-on science fiction territory, where reality gets all bendy and twisty and just defies, our everyday logic. That's right, we're talking about wormholes and time travel. I mean, who hasn't fantasized about jumping into a time machine and, going back to see dinosaurs roaming around? Or maybe zipping into the future to check out all the cool gadgets and gizmos. These ideas, they've been with us forever. They're in books, movies, late night conversations with your friends. But here's the crazy part. These concepts might not be pure fantasy. Einstein's theory of general relativity, the one that says gravity warps space and time, well, it actually opens up the possibility of wormholes. So imagine like you fold a piece of paper in half. So the two edges touch, right? Now poke a hole through the folded paper. You've just created a shortcut, a tunnel connecting two distant points on the paper. You can go from one side to the other without having to travel along on the surface. Well, a wormhole is kind of like that, but in space-time. It's a theoretical tunnel that connects two distant points in the universe, a cosmic shortcut, a bridge across, like unimaginable distances. If we could somehow create one of these things, a stable wormhole, and it was big enough, we could potentially travel to other galaxies, like instantly. No more speed limits, no more years and years of travel time. But there are some snags. Wormholes are thought to be really unstable, like blinking in and out of existence. And they might be super tiny, too small for anything to pass through. And of course, we haven't actually seen one yet. They're still, theoretical. But still, it's a pretty cool idea. Okay, so let's say, just for fun, that we could make a wormhole, a stable one, and big enough for a spaceship. Could we also use it to travel through time? Well, Einstein's theory says time is relative, right? It's affected by gravity and motion. And theoretically, if we could travel faster than light, which, according to Einstein, we can't, but if we could time travel. We could outrun time itself and arrive at a destination before we even left. So maybe, just maybe, wormholes offer a way to get around that speed limit. We wouldn't actually be traveling through space-time, but taking a shortcut around it, like bending the rules of reality to connect different points in time. But time travel? Well, it's a messy business, full of paradoxes. You probably heard of the grandfather paradox. What if you went back in time and accidentally, killed your grandfather before your father was born? That would create a paradox. Because if your grandfather died before having kids, you wouldn't exist and you couldn't have gone back to kill him in the first place. It's a real head scratcher. So how do we deal with these paradoxes, if time travel is even possible? Well, one idea is the multiverse. Remember all those bubble universes we talked about? Maybe when we travel back in time, we're not actually changing our own timeline, but entering a parallel universe, a slightly different version of reality. So we could avoid messing things up in our own past. Another idea is What if there's some kind of cosmic censorship, like a fundamental law of physics that stops us from changing the past in a way that creates a paradox? Maybe every time we try to do something that would break the rules of cause and effect, the universe steps in and, you know, sets things straight again, like a built-in safeguard, protecting its own timeline. Of course, this is all speculation. We're just playing with ideas here.
We don't really know enough about time, the universe, or how quantum mechanics and general relativity work together to say for sure if time travel is possible. And, if it is, what it would even be like. But that's what's so exciting about science. It's an adventure, a constant exploration. And those mind-boggling paradoxes, those impossible concepts, they just make us even more curious. They push us to look for answers, to refine our theories, and keep asking those big questions about reality. So as we wrap up our deep dive into the universe, I just want to leave you with a sense of, wonder and possibility. We've come so far from those ancient Greeks who thought the earth was the center of everything, to modern cosmology, where the universe is expanding, time is relative, and everything might be made up of these tiny vibrating strings. We've explored black holes, wormholes, time travel, all these amazing concepts that, challenge our understanding of what's real and what's possible. And the truth is, we've only just begun to explore. Who knows what we'll discover in the future? What new theories will explain dark matter, dark energy, all those mysteries out there? Will we ever figure out quantum gravity, unifying the very large and the very small? And will we ever crack the code of time travel? The universe is vast, it's mysterious, it's full of wonders. And trying to understand it is like one of the most amazing things humans do. So keep looking up at the stars, keep asking those big questions, and never stop exploring all the possibilities out there. Until next time, keep those minds open and keep those imaginations fired up.